Welcome to this lesson on odd and even functions. So we're going to try and see if we can identify odd and even functions by just looking at a graph and seeing its symmetry. That will help us determine if it's odd or even. And then we're going to verify if they're odd or even algebraically. So the first one we're going to start off with are even functions. Even functions, like the first graph I have shown here, they are symmetric about the y-axis. So if you have a graph where the y-axis splits the graph exactly in two halves, and one half can be folding onto the other, then the graph is an even function. What you will notice too about even functions is, like, if I have a point here at, say, let's just make up something at x equals 2, y equals 4, so I have a point at 2, 4. You would also have the same when x is negative. So when you plug in a negative value of x, your y value will still be the same, negative 2, 4. Okay, here's another example. If I have a point up here at, say, 3, 9, so I have a point at 3, 9. So my x value is 3, my y is 9. If you go on the other side, you plug in a negative x value of that. So at negative 3, you still have the matching 9, positive 9 value. So negative 3, 9 would also be on this graph. So in this case, the y values remain the same, but the x values are opposite of each other. And that means that the graph is symmetric about the y-axis, okay? That's an even function. An odd function, like I have here in the second graph, the graph is symmetric about the origin, okay? So if you move the graph around with the origin as your point of turn, then, and this point, like I have this point 2, 3 up here, would reflect and become negative 2 and negative 3. The graph is symmetric about the origin. In terms of x and y values, the x and y values are opposites of each other. So if I have this point 2, 3 that lies on the graph, then I should also have the point negative 2 and negative 3. The x value is the opposite sign, the y value is the opposite sign. That proves that they are symmetric about the origin and they are an odd. Another point too is, if you draw a line through any x and y values that are opposites of each other on an odd graph, the graph, that line will pass directly through the origin 0, 0. So like I have positive 2, 3, the matching point for that would be negative 2, negative 3. You connect those 2 points on an odd function, the graph or the line should pass exactly through the origin. That confirms that it is an odd function and that it is symmetric about the origin. And then, of course, there are going to be graphs that are neither odd nor even. They're not symmetric about the origin. They're not symmetric about the y-axis. So those functions would be neither odd nor even. How can we algebraically determine if a graph is even? If you take the original function f of x and you input or find f of negative x, and the equations remain the same, the signs in the equations are the same, then that tells you that the graph is an even function. For example, I have g of x given here, it's x to the fourth power minus 2x. Let's go ahead and find g of negative x. So we're going to plug negative x into our function and then see what happens. If the signs remain the same like our original g of x, then it is an even function. So here we go. So I take negative x and I raise it to the fourth power, and that still gives me positive x to the fourth power. I take negative x and I square it, and that gives me positive x squared. So this still remains minus 2x squared. So g of negative x has the same equation here as my g. Let's do a different color. So g of negative x is exactly the same function as g of positive x. And if that's the case, then we have an even function. All the signs remain the same. So it was a positive x to the fourth power, still a positive x to the fourth power. Was a negative 2x squared, still a negative 2x squared after I've input g of negative x, confirming it is an even function. If all the signs are opposite of what they were originally, when you find f of negative x, then that says that it's an odd function. So I'm going to find f of negative x, which means I'm going to take my function and I'm going to plug in negative x in here wherever x was, and let's analyze what happened. So we're plugging in negative x in there, negative x in here. If you take negative x and you cube it, that's a negative x cubed. So this would now become negative x cubed. And then negative times positive here becomes positive 6x. So f of negative x is equal to negative x cubed plus 6x. What about the sign changes? What happened? It was positive x cubed up there. Now we have negative x cubed. It was negative 6x. Now we have positive 6x. So all of the signs changed. All of the signs change when I plugged or found f of negative x. And if all the signs change, then this confirms that it is an odd function. So how do we know if it is neither odd nor even? If you plug in something and some signs change and some remain the same. For example, if I have h of x is equal to x squared plus 2x plus 1, and I find h of negative x, let's see what happens. So let's plug in negative x and see what happens. So when we square negative x, that still gives us an x squared, but this becomes a minus 2x and this becomes plus 1. So what happened? Did all our signs change? No. Did they all remain the same? No. This was a positive 2x and that's now a negative 2x, and that's the only change. So when some signs change, that confirms that it is neither an odd nor even function. All right. And we know that this is true because when you take x squared plus 2x plus 1, you're going to get what? X plus 1 squared, right? Or if you want to write it as x plus 1 equals 0. So we know our 0 is at negative 1. And if you do a quick sketch of this graph, let's say negative 1 is there and my y-intercept is right here. This graph is going to look something like that, right? And so it's not symmetric about the origin. It is not symmetric about the y-axis. Hence, it's a neither odd nor even function.